In this video, we're going to discuss systems of linear equations in two variables, right? And so a system of equations, any type of equations, but we're going to focus on linear equations. But a system of equations is any collection of two or more equations. Usually when we work with systems of equations, our interest is in finding out specific values of variables. And usually when you have a real life application where you have two variables that are two unknowns that you are trying to model with, then you need at least two equations to get the specific value of the outcomes that you need, your solutions. And so that is why we have systems of equations, right? Well, we're going to look at systems of equations with two variables, and basically the solution set to a system of equations in two variables is the set of all ordered pairs, all right, that satisfies all equations in the system. With that, there are some systems that don't have a solution. There are some systems that do have a solution. And then there are some systems that have multiple solutions, right? Or an infinite number of solutions. And so our goal here is to be able to solve these systems of linear equations in two variables and be able to classify them based off of the number and types of solutions that we see. And so there's this classification system that we have here for classifying systems of equations. Two big overarching things, ways to classify these systems is to classify them as either a consistent system or an inconsistent system. We've looked at inconsistent systems before, or equations before, and we said that an equation is inconsistent if it did not have a solution. Well, the same thing applies for a system of equations. If they don't have any solutions, then we call the system inconsistent. If the system has at least one solution, then we call it a consistent system. And then we can further classify that into two categories by looking at or by classifying the equations as either independent or dependent. Independent equations come from consistent systems such that the number of solutions in the system is a finite number. Now, if all of the equations that are in our system are linear, we're only going to have one solution. And so when we solve these systems and we get one ordered pair that satisfies all equations in that system, we call the equations independent. When we have dependent equations, that's a system that has an infinite number of solutions. And since there's an infinite number of solutions, we have to find a way to write all the solutions, and we usually just present the equation, right? So this reads, this says that the solutions take the form, it's the set of all ordered pairs x, y. This vertical line means such that y equals mx plus b. That's one way of writing solutions. We may talk about other ways once we get into the homework and stuff like that. Solving systems of linear equations and other systems, there are multiple ways. We're going to talk about three ways in this video. The first way we're going to get to solving systems of linear equations in two variables is to solve them by graphing, all right? So of course, we're going to graph the line that represents each equation in the coordinate plane. Each equation in that system, we're going to graph it in the same coordinate plane. And then the solution is the ordered pair in which the curve or the lines intersect. All right. So our solution is always the point of intersection, right? And so these are the possible outcomes graphically, right? Our two lines that are in our system of equations in two variables, they're going to intersect at a point, right? And that point of intersection is going to be our solution. Of course, two lines are only going to intersect at one point. This is the case where we have the independent equations, right? That's when our lines intersect. When our lines do not intersect, that means they're parallel, there is no point of intersection, which is our solution. So this system would not have any solutions. And of course, we said that means that we can categorize that as inconsistent. Now, in this picture here, there's actually two lines graphed. There's two lines graphed in this picture here, right? But we only see one line. This is because the lines are overlapping each other. Sometimes when we're given a system of equations, although the equations look different, they're probably just a constant multiple of each other. And so when we go to graph them, there actually be overlapping lines. And when our system of equation involves two equations that are overlapping lines and a solution is the point of intersection, that means since they're overlapping, they share all of the same points. That means there's infinitely many ordered pairs that are the solutions, and so we have infinitely many solutions. In that case, we have dependent equations because all of the ordered pairs that are on each of those lines, because it's the same line, is a solution. All right. And so these are the three cases, seeing them graphically. Let's look at algebraically. Actually, we're going to do this first example graphically. Yes. So solve the system graphically. X minus y equals 5, 2x plus y equals 1. All right. If we're going to solve this graphically, we're going to have to graph each of these equations here. All right. I'm going to write these in a slope-intercept form. Divide both sides by -1, right? We get y equals x minus 5, right? And so the slope here is 1. I'm going to write it so I can see my rise over my run. So I can write that as 1 over 1, and my y-intercept is -5, right? And then my other equation, 2x plus y equals 1. For that equation, we're going to solve for y. So I get y equals -2x plus 1. Again, my slope here is -2. I'm going to write it -2 over 1, and my y-intercept is 1, right? And so I'm going to graph that first line. Remember, the slope is -5. Remember, we want the point of intersection, right? Now, I don't have a ruler, and I kind of graph sloppy here. So what I'm going to do is I'm going to plot a lot of points on that line. This is not necessary if I had a calculator or if I had a way to do this on the computer. But my rise over run means I can go up 1 and to the right 1, and I'll be on that line. All right, I'm going to do this multiple times so that I'm going to go up 1 and right 1 again, up 1, right 1 again, up 1, right 1 again. And you can see I'm getting my line. But the reason I'm doing that is because I need to be very, very specific when I do this equation in my line. And so my line is going to pass through these points here. And notice here, a +1 over a +1 is 1, but a -1 over a -1 is also 1, right? So I can go down 1 into the left 1, and I'll be on my line as well. Again, I'm only doing this because I need to find the exact point of intersection. If I'm sloppy in drawing this, I might be off a little bit, right? That's why I'm doing all these, finding all these points. This one, my y-intercept is 1. My slope is -2 over 1. So I go down 2 into the right 1. And I'm going to do this multiple times. Down 2 into the right 1. Uh-oh, that's the point of intersection. By the way, just so we know, so I know my line is going to pass through these 2 points. Once I know that, I don't have to do all that stuff. But just so you know, this is the same thing as 2 over -1. So I can go up 2 into the right 1, and I'll still be on that line. So in case you needed to go in that direction, you can still do that. But here's my point of intersection here. That's where my solution is. And so the solution is the point 2, -3. And so we know that this is an independent, these are some independent equations, and I have a consistent system. All right, this is a graphical method. The issue with graphical methods is that, okay, it works good and well when my solution is like whole numbers, right? And my graphs are easy to graph, easy to plot and find, right? But when I don't have that situation, let's say our solution was something like 3/5, 4/9. That's going to be very hard to do graphically unless we have some technology to help us, right? And so we need some other methods to help us solve these systems. And then 2 additional methods, these are pretty much the other methods. The substitution method. With substitution, we're going to solve one of the equations for one of the variables and then substitute it into the other equation so that we'll have an equation with one variable. And from that equation, we can solve for one of the variables. Once we get that value of that variable, we can substitute it into one of the equations with both of the variables in it, and then we'll have both of our solutions. That's the substitution method. We're going to reduce our system of 2 equations to a basically one equation in one variable, all right? We're going to do a similar thing with the addition method. By the way, the addition method is also called the elimination method. And basically, I like using the word addition because we're going to use addition to eliminate one of the variables. So the names are, both cool. right? But basically, if I have two equations and the left-hand side of an equation equals the right-hand side of an equation, then I can add two equations together in order to get an equation that is true. But before we start to add, we're going to get opposite coefficients in front of one of the variables or for one of the variables. Meaning, if I have a 5x in one equation and I have a negative x in the other equation, if I add those together, the 5x and the negative x will cancel, right? And so that's going to allow us to reduce our system of equations with two variables to a single equation in one variable, and then we'll proceed like we did with the substitution method. All right, let's see this in action because that was a lot of words, right? We're going to solve by substitution, and then we're going to solve using the addition method. These are our two equations here, right? 4x plus 3y equals 11, negative 5x plus 2y equals 15. All right, so I'm just going to pick one equation, and I'm going to solve for a variable. I'm going to pick the first equation. I'm going to solve it for x, all right? So I'm going to take that 4x plus 3y equals 11. I'm going to solve it for x. That means I can subtract 3y from both sides. Use that. We divide both sides by 4. So I get x equals negative 3/4 y plus 11 over 4, right? So what I'm going to do is I'm going to substitute that into the equation, to my other equation for x, right? So I'm going to have a negative 5, and instead of writing x, this is the substitution step. Substitute what you had in there for x from your other equation into this equation. Okay, now when I do that, I get negative 15 over 4y minus 55 over 4 plus 2y equals 15, right? And actually, I made an error here. A negative times a negative is a positive, so I get a positive 15 over 4, and a negative times a positive is a negative. So that is correct there. Now, before I combine these y's, I'm going to get rid of these fractions here, all right, because they're going to aggravate me. I'm going to multiply both sides by 4 because I can clear fractions, and we have an equation, so I can do anything if I multiply both sides by a number other than 0, right? So I'm going to have, when I distribute this 4 to each of these terms here, I'm going to run out of space. I'm going to get 15y minus 55 plus 8y equals 60. And so I can combine those. That's 23y minus 55 equals 60. I add 55, that's 115. And then I divide both sides by 23, and I get y equals 5. All right, I get y equals 5 there, right? So now that I have this equation solved for one of my variables, y, right, which is y, I go back and I can use the fact that x is given by that, and I can substitute that 5. So that's negative 15 over 4 plus 11 over 4, which is negative 4 over 4, which is negative 1, right? And so my solution would be x equals negative 1, y equals 5. That means we have independent equations in our consistent system, all right? Now that's the substitution method. Now let's go to the addition method, right? The addition method, we start by getting opposite coefficients in front of one of the variables, right? Opposite meaning like 3 and negative 3, 4 and negative 4, 1/2 and negative 1/2, right? Those are opposite coefficients. They're opposite sides of 0, right? And so since this one's positive and this one's negative, I'm just going to get opposite coefficients in front of the x. And I want to remember, I'm going to multiply this equation by a number so that I can get the same number that's going to be the opposite of a number that I can get here. Now, 4 and 5, what you want to do is think about the multiples of those numbers, like the multiples of 4 and 5. Well, the least common multiple between 4 and 5 is 20. So if I multiply both sides of this first equation by 5, and I multiply both sides of the second equation by 4, we get a 20 in front of that x, and we get a negative 20 in front of that x, right? And so my first equation, if I do it for that term, I have to do it for every single term on both sides. So I'm going to get a 20x plus 15y equals 55. And then here I get a negative 20x plus 8y equals 60, right? And so with that being said, we can go through and we can add our equations together. Well, they cancel. I'm going to get 23y equals 115. Divide both sides by 23. I get y equals 5, right? Now that I have that, I can go to either of my equations with both of those variables, plug in that 5 for y. I get 4x, this is 15. Let's subtract 15 from both sides. We get x equals -1, right? And so we get the same solution. One method is easier than the other. This addition method is probably easier because we don't have to worry about fractions, but you can see the substitution and the addition method. Remember when we do the addition method, we add the opposite coefficients to eliminate one of the variables so that we end up with an equation with one variable. Over here, we solve one equation for one variable and substitute it into the other equation so that we can get an equation with one variable. So we reduce the system of two equations and two variables into a single equation in one variable. You can substitute to do that, or you can use addition to do that. This example here, I want you to do on your own. I'm going to tell you that this is an inconsistent system. I want you to use any method. You can use the addition, the graphical, or the substitution method. I want you to go through the process of showing that this system is inconsistent. Instead of doing this example, I want to give you an example, and I didn't put it in your notes, of solving this system here, right? So we're going to say like example 4. Let's do 3 prime. 3 prime. We have this system here, 0.05x plus 0.1y equals 0.6, x plus 2y equals 12, all right? So we're going to solve this system here. You have any method you want to use, right? What I'm going to do, I know we don't have calculators in this course, and so you're probably like, well, why are we doing decimals, right? Remember, you don't have to work with decimals, right? You can always, since you're dealing with an equation, you can come up with an equivalent equation by multiplying so that you don't see decimals. The term with the most decimals here is this one here, and it has 2 decimal places, right? So that means if I multiply both sides of this equation, by 100, that means this gets multiplied by 100, this gets multiplied by 100, and that gets multiplied by 100. I'm going to end up with the equation 5x plus 10y equals 60, all right? And then my second equation stays the same. It doesn't have any decimals. Now, all I've done was I've gotten rid of the decimals. I've not done the substitution, graphical, or substitution method, right? What I'm going to do now is I'm going to use substitution. Right, because this equation right here is very easy to solve for y. Solve for x. Because all I have to do is subtract 2y from both sides. And so now I can substitute this negative 2y plus 12 in the other equation for y, right? So I'm going to get 5 times a negative 2y plus 12 plus 10y equals 60, right? So I replaced that here and kept everything else the same. I distribute my 5, so I get a negative 10y plus 60 plus 10y equals, that should be a 60 here. And guess what happens to the 60s? Sorry, the 10y and the negative 10y, they cancel. And so we're left with 60 equals 60, which is always true. And when we said that we had an identity equation, that's what we said when we have a equation with just one variable. And identity equations have infinitely many solutions. All right, I should just put a space there. Infinitely many solutions, right? Well, this means that this system is dependent. And so there's an infinite number of solutions. So I can't write my solution as a single ordered pair like this. Actually, we can. I'm going to show you. And so what we do is we say that our solution set is the set of all ordered pairs, x, y, such that, all right, we can go to one of these equations and put it into, I'm going to use this equation since it doesn't have decimals here, and just such that x plus 2y equals, what was that number? 12. All right. An alternative thing to do is to write it as an ordered pair, our solution as an ordered pair. All right. But instead of writing it as x comma y, we solve this equation for y. For instance, if I solve this equation for y, I'm going to get y equals negative 1/2 x plus 6. And so instead of writing it this way, we can write our solution as x comma y given in terms of x. Well, I solved this equation for y, right? I subtract x, I divide it by 2, and I know that y is always equal to negative 1/2 x plus 6. And so this gives us an alternative way of writing our solution, okay? X comma 1/2, negative 1/2 x plus 6. That way, if anyone gives you an x value, you can plug it into here and you can plug it into here and you can quickly calculate what one of the solutions will be. All right. Alternatively, you have to graph this line in order for you to get all of your solutions. So sometimes you'll see your solution written this way, and sometimes you'll see your solution written this way. All right. Last but not least, we're going to look at an application problem. And this application problem is the prime example of why we want to use systems of equations, right? It says a total of 76 young Republicans attended a strategy meeting. The number of females exceeded the number of males by 2. How many of each gender were at the meeting? And so what we would normally have to do is write an equation, right? So I'm going to M equals the number of males and F equal the number of females. And so since 76 of those young Republicans attended the meeting, I know that if I add the number of males to the number of females, we should get 76. Now, I want to find out what F and M are, right? Usually when you have an equation, two variables that you need to solve, you need two equations. And we give you enough information here to create the other equation. It says the number of females exceeded the number of males by 2. Well, we don't know what the number of males was or is, but if I add 2 to that, I get the number of females, right? And this should be a lowercase f. And so I have two equations and two variables, right? And I want to solve this system in order to help me find out the number of males and females. Well, this is set up perfectly for the substitution method because it has f already solved for. And so I will go and take this m plus 2, substitute in for f in that first equation there, and I'm going to get m plus 2 equals 76, or 2m plus 2 equals 76. 2m equals 74, divide both sides by 2, and I'm going to get m equals, is that 37? And so now that I know my m, I can substitute it back into this equation, and meaning add 2 to it, and I'll see that I get 39 females, right? And you can check yourself. The number of males is 2 units more, and if I add these numbers together, I get 76, all right? So this concludes this video. Remember, work through this problem on your own to make sure that you can see why that is inconsistent. All right, and that's it for this video.